Hey everybody, this video is going to be on section 5.2, which is about binomial probability distributions. So a binomial probability distribution is a type of discrete probability distribution, which is what we learned about last class, that comes from a sequence of trials that satisfies the following properties. So first, there are a fixed number of trials. Second, the results of the trials are independent. So basically that means if one trial comes up a certain thing, then that would not affect the probability of that occurring the next trial. The third thing is that each trial has all outcomes that can be classified into two categories, usually success or failure. So sometimes you may be doing a trial that has multiple options, but multiple of them you can kind of categorize as like failures, and one of them you might consider to be a success. Like for example, an example we're going to get into later with like multiple choice questions on a test. There may be 5 choices that could occur, but maybe only one of them would be considered a success and the other 4 would all be considered failures. You know, being the success the one correct answer, and failure the 4 choices that would all be incorrect. And Property 4 is that the probability of success remains the same for all trials. So that's kind of like similar to the independent property, whereas a binomial probability distribution wouldn't be valid if for some reason a later trial would have a different probability of success than an earlier trial. Okay, so some notation here. P, lowercase p, is going to denote the probability of a single success. So on just one trial, what was the probability of success? Alright, I apologize. I just had to pause to bring a drawing utility into my screen. So like I was saying, I was talking about notation. So P denotes the probability of a single success on one trial. So doing the thing one time, what is the probability of getting a success? Q is going to represent the complement of getting a success, or the probability of a failure, which is always going to be given by 1 minus P. N is going to denote the fixed number of trials that we mentioned before. The number of trials have to be fixed ahead of time. So N is how many times you're doing this procedure. And X is going to denote the number of desired successes you're looking for. Okay, and basically we're going to use the binomial distribution to find the probability of getting exactly X successes, or maybe at least X successes, or maybe X or fewer successes. So an example that comes to my mind immediately is I like playing basketball. So let's say I have a probability of getting a 3-pointer in of I have a 30% chance of getting a 3-pointer in. So the probability P of getting any given shot in would be 0.3. So then the probability of me missing would be the complement of that, 0.7. Okay, so that's what my P would be. That would be my Q. And I may be interested in seeing, well, if I shoot 10 of these shots, what is the probability that I get in 5 of them? And so in that case, N would be how many total shots I attempted, which would be 10, and X would be the number of successes I'm interested in seeing if I can hit. So seeing what the probability of me hitting 5 of those 10 shots would be. All right, so that's an example of some of the notation here. And here's some notation used in the textbook. P of X given N, comma P denotes the probability of getting exactly X successes in N trials with a probability of P for the success. All right, so let's move on to an example. So you're taking a 15-question multiple choice quiz, and each question has 5 options, A, B, C, D, and E. I'm sure you guys can imagine this. So now suppose you had no idea what was on the quiz. You didn't even know there was a quiz coming up, so you just randomly guessed letters for every question. Let X denote the number of correct guesses. Verify that X follows a binomial probability distribution and determine N, P, and Q. So the first thing going back up here is are there a fixed number of trials? Yes, there were 15 questions, and each of these questions is an iteration of basically, did I get this question right or wrong? That's the whole success/failure thing about this binomial, the two options, success or failure. And yes, there are 15 questions, so n equals 15 is the number of trials. Second question, are the results of the trials independent? Yes, because the outcome of one question doesn't affect the probability of getting another one correctly, right? Like if I randomly guess B for question 1, if I happen to get that right by pure luck, that doesn't mean I'm either more likely or less likely to get question 2 right or wrong. Part 3. Does each trial have outcomes classified into 2 categories? Yep, you either get the question right or get the question wrong. There's only one thing that'll be a success, getting it correct, and there are 4 options that would be incorrect or a failure. But you have these 2 essential categories, correct or incorrect, which would be your success or failure. And is the probability of success, does it remain the same for all trials? Yes, since all questions have 5 options, and only one of them is going to be correct in any of them, the probability of success is always 1 out of 5, so that's your P, and therefore your probability of failure would be 4 out of 5, or Q, which you could express as decimals as Q equals 0.8 and P equals 0.2. Now, something that can get tricky here is when you sample from a population without replacement. So like, for example, with a deck of cards with 52 cards, if you picked one card out and you found something to be true about it, and then you put it aside and picked, you found the probability of getting a jack, let's say, and that probability was 4 out of 52. And you put that card aside, now your probability of getting a jack the second time would be different, because you only have 51 cards in the deck, not 52. So that's sampling without replacement. Now, when you sample without replacement, the trials become technically dependent, like we saw right there, which would violate this property of the binomial probability distribution. Now, it turns out that this can be mitigated when the sample sizes is less than or equal to 5% of the population size. So we're going to consider trials to be independent when that's the case. It's called, I forget what it's called, the rule of cumbersome calculations. And it turns out to be, virtually mathematically identical. So we can consider them to be independent in those cases. All right, so your turn now. Give this example right here a try, and then when you finished, pause the video right now to give it a try, and then replay it after to see if your answer matched up with mine. Okay, so let's verify that it follows the rules of the properties of a binomial probability distribution. So the first one is that there have to be a fixed number of trials. Is that the case? Yes, there is. You have 20 trials, and that's how many you selected, so that's what we're going to operate with. So 1 is all set. 2, is it independent or not? Well, actually, technically, it's not independent, because as you pull cashews out, there were 60% to begin with, so if you pull cashews out, you would expect that the remaining percent would now be less than 60%, and so on. So the only way we can get around this is using what we call that rule of cumbersome calculations that I mentioned in this convention up here. And so that would mean that the sample size 20 would have to be less than 5% of the whole population. So I guess that would actually really depend on how huge this can of mixed nuts really is. So let's assume that it's big enough, huge enough, such that 20 would be fewer than 5% of the entire thing. If that's the case, then we could say it is, at least in practice, independent. So part 3 was that each trial has to be classified into 2 categories, success and failure. That is true here, right? We have basically 2 categories. Cashew is one of them, and that would be kind of considered the success. And the other one would be, well, there are many different types of nuts, but we can classify all of them together as not cashews, which would be considered the failure. And part 4, the probability of each success remains the same for all trials. Well, if we're operating with this understanding of independence, or this kind of agreeing of a virtual independence, then we can say, yeah, the probability remains the same. There's no reason to think that, if I pull out 20 nuts and look at the first one and find out if it's a cashew or not, the probability would be 60% chance that it's a cashew. There's no reason to believe that the 19th cashew would have any different probability. So yes, the same. All right, cool. So let's move along then. So here is the formula for calculating binomial probabilities. So it's right here in this box. And a little heads up, we're not going to be using this formula right here by hand. We can use our graphing calculators. They have a function in them that will calculate binomial probability. So we really don't need to be doing this by hand this semester. But the formula is to find the probability of exactly x successes in n trials, and where each trial has a probability of success of p, then the way to find that probability, that overall probability of those x successes, is you take what's called n factorial and divide it by n minus x factorial times x factorial, and you times that by p raised to the x power times q raised to the n minus x power. All right. This factorial thing, this exclamation point, you may be wondering what that is. So that is a mathematical symbol, and it denotes the product of decreasing integers. So an example right here should clarify it. 6 factorial equals 6 times 5 times 4 times 3 times 2 times 1. So it's basically a product of all the integers less than or equal to 6. That's what factorial means. Right? And in addition, a little note that 0 factorial we always define as equal to 1. So the fraction portion of this formula always will reduce to a whole number if you expand the factorials and cancel the terms out properly. All right, so let's see an example. So you're taking a 15-question multiple choice quiz. Each question has 5 options, A, B, C, D, or E. Now suppose you randomly guess at every question. What is the probability that you get exactly 2 questions correct? So we know that the P is 0.2 because there were 5 options. And what's the probability if you're going to guess and get one correct? It's 1 out of 5, which as a decimal is 0.2. And therefore we know Q, which is the complement of that, is going to be 0.8. Okay, so we have P equals 0.8, P is 0.2, Q is 0.8, N, which is the number of trials, is how many times you're going to be guessing over and over and over again, which is 15 times, and X is the desired number of successes, which we're interested in exactly 2 questions correct. So you plug these 4 numbers all into this big formula up here, and you're going to get n factorial, which is 15 factorial, divided by n minus x factorial. Well, what's n minus x? N minus x is 15 minus 2, which is 13. So 13 factorial times 2 factorial, and then you're going to times that by p to the x power times q to the n minus x power. So that's going to be p 0.2 to the x power, which is the second power, times q, which is 0.8, to the n minus x power. And n minus x is 15 minus 2, which is 13. So this right here, this expression right here, is going to give you the probability of getting exactly 2 questions correct on this test. So let's expand out the 15 factorial that we said is going to be 15 times 14 times 13 times da 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 all the way down. And you divide that by 13 factorial, which is 13 all the way down, times 2 factorial, which is times 2 times 1. So what happens here is a lot of things cancel out. You have these products of 13 that cancels with a factor of 13 over here, 12 and 12, 11 and 11, 10, 10, 9, 9, 8, 8. All these numbers cancel out. And basically all you're left with is 15 times 14 divided by 2 times 1. And so you'll see that carried over down here. And times 0.2 to the second and 0.8 to the 13th. So you plug all this into your calculator and it'll give you this probability right here, rounded properly to 3 decimal places. All right, so the probability of getting exactly 2 questions correct is 0.23. So you got about 1 in 4 chance of getting exactly 2 out of the 15 questions right, which would be really bad, of course. All right, so now you try one. So try to find what the probability is that you get exactly 4 questions correct. Pause the video, give it a try, and then when you replay it, we'll see my work and you can see if yours matches up. All right, so we're trying to find the probability of 4 successes given 15 trials with a probability of each success occurring still at 0.2. So you could set it up this same way as before. You know what? I'm actually not going to go ahead and do that all out. What I'm going to do is I'm going to show you guys how to use the graphing calculator to figure this out. So in the graphing calculator, there's you can go to this little area right here called distributions. So you can press second vars, and that'll bring you to the distributions menu. And we can go all the way down to click on something called binom PDF. Binom PDF. So a binom PDF. There is also a binom CDF, but for this example, we're going to use PDF. All right, and you put in how many trials you're doing, which was 15 trials. The probability of success on any given trial was 0.2. And the x value is 4. It's the number of desired successes. So we press paste, then we press enter, and boom, it gives us the probability. So if we're going to round this to 3 decimal places, we'd say 0.188. So 0.188. All right, cool. Great. So also in the back of the textbook, we have these things called binomial probability tables, which you can use these. You'll see they basically give a kind of a guide for probabilities. It's like if you have 2 trials, basically you can find out the probability of getting exactly 0, 1, or 2 successes in those trials if the probability of success was any of these numbers right here. But is not so useful when your probability of success was not one of these things right here. So I would say we're not going to use these tables this semester. So let's skip over those. We're not even going to talk about these tables. Forget them. Okay. So now let's discuss how we can use probabilities to determine whether a result would be considered unusually high or unusually low. So we say a number of successes is unusually high if the probability of getting that many or more successes is smaller than 0.05. We say something has an unusually low number of successes if the probability of getting that many or fewer successes is less than 0.05. All right. So let's do an example to exemplify these. So we'll go back to our multiple choice quiz example down here. And suppose you're taking a multiple choice quiz. There are 15 questions. Each question has 5 options. Suppose you randomly guess at every question. use the binomial table. We're not going to use the binomial table to answer the following questions. Would 6 correct answers be an unusually high number of correct guesses? So, first of all, I want to ask you guys a question, and that is, how many questions, if this was written in some alien language, you had zero idea, no way of having any clue about any of these questions, and you had to, for 15 of them, you just had to randomly choose some choice A, B, C, D, or E. How many questions would you expect to get right on average? Well, the probability of getting any question right would be 1 out of 5, so 0.2. Right? And there are 15 questions, so you'd expect to, of these 15 questions, you'd expect to get 20% of them right, because there's a 20% chance of getting any question right. So you take that 20%, times it by 15, and you would expect on average to get 3 questions right. If you think that you would get more than 3 right, then I think you are a little bit overly arrogant about your own abilities. So, would 6 correct answers be an unusually high number of correct guesses? Well, it definitely would be above average, but would it be unusually high is what we're trying to find. And this unusual figure we're basically going to define as having a probability of occurring of less than 5%. So, what we have to do is find out whether the probability of getting 6 or more correct questions correct is higher or lower than 5%. So, so you need to find what's the probability of getting 6 questions right, what's the probability of getting 7 questions right, 8 questions right, 9 questions right, and so on. So I'm going to write a little table down here, and it's going to be a little probability distribution table, just like we did last class. All right, so all of our options, we got 0, 1, 2, all these 15 questions, and we could get any number of these correct. So down to 6, all the way down to 15. And all of these situations are all going to have different probabilities of occurring. So what we're interested in is all of these probabilities right here, from 6 all the way to 15. Is the probability of all of these probabilities added up greater than or equal to 0.05? Well, the probability of getting exactly 6 correct, you could either use the table like the problem offered, or you could use the calculator and find binom PDF of 15 trials, probability of 0.2, and what's the probability of getting exactly 6 correct? It is 0.04299 blah blah blah. Alright, so then you'd want to find the probability of getting exactly 7 correct. A little shortcut here, and that is 0.013819. And you'll see these all truncated to 3 decimal places and written here. You can do it again with 8. Oops. And you get 0.00345 and so on. So you take those, you add them all up, and you find out whether they were bigger than 0.05 or not. And it turns out the sum of all these turns out to be 0.061. So since this is not smaller than 0.05, it's not less than 5%, we would not consider this to be an unusually high number of successes. All right. So what about 7 correct answers? Would that be an unusually high number of correct guesses? Why don't you guys try to figure that out on your own, and then press play to see if your answer matches mine. So you could have done this the long way and added them all up again, or hopefully you guys were able to use a little intuition and think that, all right, if all of these, I'm trying to find out whether 6 correct answers would be unusually high. Now the last example I was trying to find out whether 6 would be unusually high. Now I'm trying to find out whether 7 would be. So this question is very similar to the last one. Really, I'm just excluding one of my choices, right? I'm just excluding this 6 now, right? Well, if all of these probabilities were equal to 0.061, and I know the probability of 6 exactly was this, we found on our calculators, right? Then what's the probability of all of these from 7 to 15? Well, it's going to be 0.061 minus 0.043, which is going to turn out to be 0.018. So the probability of getting 7 or more correct answers is 0.018. And that is a very low probability of occurring. And it is less than our threshold of 0.05. So we would say yes, it is. Yes, it is unusual. All right, cool. So let's go on to our next example. Example of unusually low number of successes. A huge can of mixed nuts contains 60% cashews. You randomly select 20 nuts. Would 6 cashews be an unusually low number of cashews? So the way we determine this is we need to find the probability of getting 6 or fewer cashews. Add up all those probabilities and find out if it's greater than or less than 5%. So I'm going to show you guys a way to do this in the calculator. And this is going to be using a different function in the calculator, and we're going to clarify this and solidify it in class. Now we're going to use what's called the binom CDF function. So the binom PDF function that we used earlier finds the probability of getting exactly however many successes you put in. So, exactly 8 successes. Now the binom CDF function finds the probability of getting this many or fewer successes, which is really helpful because that's actually what we're interested in right now. We're finding the probability of 6 or fewer successes. So instead of having to find all these probabilities for 6 and 5 and 4 and 3 and 2 and 1 and 0 and adding them all up, we can just do this in one calculator stroke by going to distributions, then going to binom CDF, and again we're going to clarify in class and really solidify when to use PDF or CDF. So CDF again is, and C stands for cumulative. That's why we use this one here, the cumulative density function. So we're again doing, so here we're doing 20 nuts, so that's our number of trials. The probability of getting success in any given one is 0.6 because we said there's 60% of them are cashews. And we want to find with CDF the probability of getting 6 or fewer successes. We're going to let x equal 6. So we paste, and boom, we get 0.00646 blah blah blah. So you can see this is a very, very small probability, certainly less than 5%. It's less than 1% even. So therefore, we have a probability of about 0.006, which is a very small probability. So it is smaller than 0.05. So yes, we would consider this to be an unusually low number of successes. All right, and you can pause the video and try this one. And when you replay, you'll see my work, or you can just let it go and keep following along. So, would 9 cashews be an unusually low number of cashews? Well, I'm going to use my binom CDF function again here because I'm doing unusually low. So I'm trying to find whether the probability of getting x is less than or equal to 9. I'm trying to find out whether this is smaller than 0.05 or bigger than 0.05. So I can find the probability of 9 or fewer cashews by using, again, my binom CDF function. So I'll go down quite a bit. Binom CDF. Again, 20 trials. Probability of success is still 60%. And now I'm doing 9 or fewer. So I'll put that in for my x value in binom CDF. I'll paste it, and I get a probability of 0.1275. So if I'm going to round this to 3 decimal places, it would be 0.128. All right. So therefore, we compare this to 5%. Is this bigger than 5% or less than? It's bigger than, so therefore, no. We would not consider this an unusually low number of cashews. It's less than we would expect, right? How many would we expect? Well, we would expect 60% of these nuts to be cashews, which would be 12 of them. And 9 is certainly less than that, so it's less than we would expect, but it's not what we would say an unusually low amount. Oh, I missed a U somewhere in here. Unusually. Okay, cool. All right. Beautiful. All right, so that's the video on 3.2. Hopefully this made sense. And if you guys have questions, of course, as always, please bring them to class, and I'll see you there. Bye.